I'm Frank Casano. I'm the chair of the math department. There we go, Sam. Right on time with that. We're thrilled that you all could come for a spectacular night that our students put together. This is, we help out as much as we can, but this is something that they want to do and they dive into. So everybody that's here, people here on Zoom, we're so happy that you can be here. Just to give you a little bit of Math Night history, this event was started by former math teacher Rich Clear, who is here tonight, right? There we go. And it's remained an annual event, and it is crazy to put together, trying to get everybody to get their act together before spring break. Where we're together at lunch yesterday and today, like, ooh, are we gonna have a math night? But we have it, and it's exciting. So, and you're in for a real treat. Before we begin with our first presentation, I just want to give a huge thanks to everybody that's here, but really my team, Rachel, Kevin, Anya, Taylor, Ian, Josh, Jamie. You guys are just helped me out so much this year, my first year as chair, and I really appreciate it. So to get things started, I'm gonna call up Jamie to introduce our first group. Thank you.
My name's Jamie, and I got to work with Eric and Luna as they were preparing their presentation, and I gave them a tiny bit of feedback, but all the energy that I'm sure that they will bring is amazing. And as you can see on the screen, they're going to share a little bit about some intuitive and not so intuitive construction. So give it up for Eric and Luna.
Hi, so I'm Luna. That's Eric, and like Jamie said, we're going to be talking about unintuitive constructions. So first, what is a construction? A Euclidean construction uses a compass and straight edge to create mathematical figures. And so, like I mentioned, a compass which draws circles and arcs, and a straight edge to draw lines, straight lines.
To get a sense of this, we'll get a little demonstration here. So we're using two tools. One of them is a straight edge, which will allow us to draw straight lines. Imagine we have an infinite sheet of paper, this will allow us to draw an infinite long line. And the other is a compass. So with a compass, we give it a center point and a place for to lie somewhere on the outside, and it'll draw a circle there. And as a brief example of something useful that can be done here, I have this line here with 2 points in it. Let's say I want to find the midpoint of that line. So one way I might do that would be to construct this circle. One more circle here. And then I could put a line between these two intersection points. And the intersection where the two lines are in the center will be the exact midpoint of that segment.
Great. So Eric is now going to hop over to the second little demo. Great. So here we're starting off with a square, and what Eric is doing the same exact thing that he did on the first demonstration, which is finding the midpoints of each of the sides of the square using the construction he just showed, which is the perpendicular bisector. So he's finding the midpoint of each of them, doing a circle where this square is inscribed, and at each of the intersection points between those new lines, you will soon see that it forms a regular octagon. Yay! There we go, regular octagon. So briefly as a thing to make things easier as we go forward, when I say a regular polygon, I mean that all of the sides are the same length and all the angles are congruent or the same. And another way that we can refer to polygons is by the number of their sides. So instead of saying octagon, we can also call it an eightgon. This will get, it'll be more useful when we're using larger numbers that we don't actually know the names of, like 17 or 37 or wild numbers like that. So yeah,
This example, I went from a square, which can also be called a fourgon, although we are familiar with squares, we say squares, to an octagon, which has 8 sides, an eightagon. And using the same process, bisecting each of the sides, I can get a 16-gon, a 32-gon, etc. And we'll have an infinite number of polygons we can construct.
Double each time. All right, so now you get a little introduction. We're gonna test your intuition. So I'm gonna ask you to raise your hand if you think that it is possible to construct each of these with a compass and straight edge. You might have gotten a couple hints from trying to construct the things outside. So here it is. Okay, raise your hand if you think you can construct a regular pentagon. Okay. What about a regular hexagon? Okay. What about exactly 1/3 of an angle? So trisecting an angle. Okay, what about a line with the length of √2 + 3 √5? Great. Now let's check if you were right. So
On the left here are the 2 polygons, both of which are possible. The hexagon comes out of the packing of circles and has some really pleasing symmetry with how all the circles nestle together. The pentagon construction is far less intuitive, but just as possible. And so this is an example of one set of lines and one set of circles that will create a pentagon. I can't articulate a nice reason for why it's exact, but it ends up being exact. And if you run the calculations to the actual coordinates, that ends up being the case.
So for the line with the length of √2 + 3 √5, that might sound like a very weird length, and the construction does look a little bit complicated, but it's all based on the fact that there are 2 triangles, one of which has the sides of 1 and 1, which is giving you √2, and the other one has a side length of 2 and 1, which gives you √5. This is showing that you can make any square root just using the Pythagorean theorem, and you'll get a line of that length.
What's really powerful about this type of construction is we've given an arbitrary √2 + 3 √5, but it turns out that any length that you can write using any combination of addition, subtraction, square roots, division, multiplication, you can also construct, which is kind of cool.
And last but not least, trisecting an angle, despite the fact that it actually seems quite simple, is about as impossible to construct as that elephant up there. So quick plug for Euclidia. Eric found this app. It's really cool. You can it allows you to do compass and straight edge constructions just on your phone. It gives you a whole bunch of puzzles like we had outside, and yeah, it's just fun. You get to play around with trying to do it in the simplest way possible. Hashtag not sponsored.
I do highly suggest this or experimenting with the physical compasses outside. There's really no substitute for actually messing around and exploring them, because it's really hard to get an intuition for how you can build things unless you manually go through the process. 2 things to keep in mind as we move forward. 1, it's easy to show some possibilities for what you can make. So we know that a hexagon is possible. We can use the doubling trick to get 12 sides, 24 sides, etc. But it's very difficult to prove exactly what is and isn't possible to construct. So if I pose a question like, is a heptagon constructible? Well, if I had a way, I'd be great. But if I don't have a way, I don't have a good way of reasoning. And as we've seen, the intuition for whether something is or is not possible is really, really flawed for us humans.
Well, okay, origami. If you guys came to math night last year, you know that I like folding things. So so here I am again talking about origami. So when we were talking about construction, Euclidean constructions, we were talking about using 2 tools: a compass, which makes circles, and a straight edge, which makes lines, right? With origami, we only have straight lines. You can't fold a circle. So intuitively, origami would be a less powerful way of creating shapes and constructions. However, this actually is not the case. But before we show you why that is, Eric will hand me that paper. So with this, I'm gonna show the same construction that Eric did at the beginning, the perpendicular bisector, but using origami instead of using the compass and straight edge. So the way we go about that with origami. So here we have the solid line with 2 points on it. If we match those points up, I'll hold it up to the light and crease that, we will end up with the line that is the perpendicular bisector. So that is an example of a simple proof of origami. But now we'll move on to
The ultimate move.
TM.
Whoa, it's so powerful. So whiskers.
You probably.
What's the pretty things on it? So here we have 2 points in dark blue, and we have 2 target lines. And so the ultimate move
TM.
is going to be to find some fold that will map this point onto this line somewhere, and this point onto this line somewhere. So we have a demonstration of what this looks like. This is the same setup. Let's look at the top point and the yellow one. Right now, it is being reflected to this yellow point here. And you can see that there's any number of lines here that reflect the point to any number of locations on the horizontal line. And so there's a whole set of folds that would do this. Similarly, for the green line, there's a whole set of folds that'll map it somewhere on this vertical line. However, if I want to find one fold that'll do both, I'll have to match the 2 lines here. So I'll fiddle around a little here, until we get it. Close enough. So we've gone from this whole set of any number of 2 lines down to 1 that matches all these.
And this is the move that is impossible to do with a compass and straight edge, but is possible with origami. So one way to think about why this is possible with origami, but not with, or why it's more powerful, this move is more powerful than other moves you can do with a compass and straight edge, is that a compass and straight edge involves 2 inputs. There's 2 points that a line goes through, or a point in the middle and a point on the edge of a circle. With this, we have 2 points and 2 lines, which makes it more constrained and more powerful.
Whoa, scary math.
Scary.
So another way of looking at this is, say we want to construct the 7-gon and the 17-gon. One method of doing so would be to find the exact locations to each of the points. And so I can choose 1 point here and write out the x coordinates I want to find. If we switch over to algebra land, we'll get this scary expression for the exact x coordinates of that point. And what's interesting about this is it uses cube roots in it. At the beginning with the root 2 plus the root 5 example, we showed that compass and straight edge can construct anything using square roots and arithmetic operators. However, this one is cube roots. And because you can write with cube roots and there's no way to translate that to square roots, you know that this is something that you won't be able to do with compass and straight edge alone. Compare that to the 17-gon here, which even more scary math. However, only square roots and arithmetic operators. It doesn't have the cube roots that the 7-gon does. And so it can be done with only compass and straight edge.
The fun thing about origami is that you actually can solve those or do those cube roots. And that is how you end up with folding a regular heptagon in just a few steps. It's actually quite a simple construction with origami, and it's impossible to do with a compass and straight edge.
So this leads to the question of which numbers of size are you able to construct or not construct? So we're going to briefly talk about. He looked like that too.
Fermat was a mathematician who lived in the 1600s. He made important advances in several areas of math, including number theory, analytic geometry, and calculus. He's often referred to as the father of modern number theory, which is like work with prime numbers.
We call any prime that can be written like this a Fermat prime. And so he originally worked with these. And these are the first couple he came up with. After that, they get large quickly. And so he didn't go past this. And there's a funny story here in that Fermat is experimented with these. He found the first couple work. So if you plug in n equals 0 here, you get 3. You got plug in n equals 1, you get 5, etc. And he found the first 5 cases, which are all primes. Everything larger than that was too big for him to practically mess around with time. And he conjectured, well, they all must be primes. Coming with today's mathematics, we found that every single other one we've tested is not a prime.
So even a great mathematician should not trust his intuition.
That concludes our presentation.
We heard it too, I guess.
All right. Almost. Good evening, everyone. I'm Josh. Frank and I had the pleasure of working with our next presenters, who chose to use their mathematical expertise to try and gain a competitive advantage at the game GeoGuessr. They started out with what seemed like a pretty simple problem. It got complex really quickly. We were very impressed with how they stuck with it, worked hard, stayed curious, and ultimately have created a presentation where they've broken it down into ways that we can all understand their solution. So whether you're a GeoGuessr fan or not, you're in for a treat. Please welcome Victor and Sam.
Yeah, hello everyone. Today we'll be unveiling GeoHedger, a tool to mathematically optimize guesses in the world's most competitive geography game.
First, let's introduce GeoGuessr, the game off of which this entire project is based. GeoGuessr is an online geography game based around determining the location of an image taken from Google Street View. After looking and moving around, a player makes a guess on a map as to where they think they are. A score is then given out of a maximum of 5,000 points based on the distance your guess is from the true location. As well as having a variety of game modes and maps, GeoGuessr has a thriving multiplayer scene with a leaderboard composed of hundreds of thousands of regular players, making it indisputably the world's biggest geography game.
So, central to the concept of GeoGuessr gameplay is the idea of a GeoGuessr meta. That's an obscure clue in your surroundings that can help give away your general location, often your country. So let's look at a few examples. Here's a typical European Union license plate. You can see there's a little blue stripe here that you can see despite the Google Street View blur. And that's common to all cars in the European Union. However, in Portugal, there's this extra little yellow strip that you can see here. So if you're ever either playing GeoGuessr or just on Google Maps or in real life, and you see this yellow strip, that car is from Portugal.
Another example is this car. This car is only driven in Mongolia. And if you're in Mongolia, you can see this car from the Street View there.
That's the Google Street View car that was used to take locations in Mongolia. And then for a final example that's closer to home, you might recognize this image. There's one thing that's in common between these two places in California. It's pretty obscure, but see if you can locate it. Let's see if I can see it. Yeah, Luca?
Three stripes on the pole.
Yeah, both these poles have 3 stripes on them. And it turns out that this is a thing unique to California. Californian poles all have 2 or 3 little reflector stripes on them. All other states in the US only have 1 stripe. Meanwhile, most other countries just don't have those stripes at all. So these are only a few of the tens of thousands of metas that exist in this game. So if you're a GeoGuessr player, what does this all mean for you? It means that a lot of the time, figuring out what country you're in is really trivial. So let's see this in action. Suppose we're in GeoGuessr and we get this location. Somebody tell me what country we're in? Quick memory test.
Oh, yeah.
Great job. So I'd like a volunteer to describe this location for me in as much detail as you possibly can. Anyone? Really boring? Why? What makes it boring?
It's really
What? What else? What's the road like?
Civilization.
No civilization. What's the road like?
Unpaved.
Unpaved dirt road. What's the shrubbery like?
There's
Well,
shrubbery.
Shrubbery, yeah. Low shrubbery. Now let me give you one more, also from Mongolia. You can see it's pretty much the same thing. There's also the shrubbery. There's unpaved road. It's really flat. There's nothing in sight. It's panned down so you can see the car, but if you pan up, there's still nothing going to be in sight. So you'd expect these to be really close to each other since they look so similar. Let me show you where they actually are. Here's one, here's the other. As you can see, they're as far apart in Mongolia as you can get. This distance is over 1,000 miles, which is almost half the diameter of the US. So if you're playing GeoGuessr, you think it's here, you guess here, it turns out it's actually over there. That's going to give you a score of only about 1,500 points, which is pretty bad. In fact, it's so difficult to region guess in Mongolia that there's a 200-page long Google Doc that's been translated into multiple languages. That's all about how to guess in Mongolia.
Now,
Oh,
how do
go ahead.
Now, how do GeoGuessr players overcome this challenge? Well, they hedge their guesses, trying to account for all possible locations. For example, knowing that a location here might look identical to one here, which might look identical to one here, a player would try to guess roughly in the middle. Not only is this a safe guess, but due to the way that the point scoring system works, it actually nets you more points on average than a risky guess to the side. Now, for Mongolia, hedging is quite trivial. Obviously, you should guess right here, as there is a ton of street view locations there, and it's roughly in the middle of everything. However, hedging isn't always this easy. Let's take a look at a country where this is much harder, Australia. In blue are all the locations within Australia where there can be street view coverage. That is, all places where a round's true location can possibly be. So if the only thing that you know is that you're in one of these points in Australia, where would you guys choose to hedge a guess?
Anyone? Just give me roughly like relative to a city. Where? Between, actually,
Right, where it says and stuff.
Yeah,
Ours is
exactly.
near South
Yeah,
Wales.
like towards
Yeah.
the right, but not on the coast.
right?
Yeah.
That's a great intuition, and it sounds about right. However,
Yeah.
however, we want to find an exact coordinate at which to guess, something that is mere intuition cannot do. Not only that, but we want to prove that this hedge is optimal. Here's where GeoHedger comes in.
So here's the central problem that we just described, all written out. Where's the optimal place to hedge a guess? Again, hedge, you're trying to get the average best score. To maximize its average point score across all possible locations. Every place where you could possibly be. So to start, let's imagine we have some mystery function f. Because we want to make this all mathematical so we can actually evaluate it. This is math after all. F is going to take as its input some location. Well, what is this location? It's just some location on our globe. What's another way to say a location on our globe in more precise terms? Yeah, coordinate. What are those two components? Right. So instead of that, we can just say latitude and longitude. So we plug this into our mystery function f. We don't know what it is yet. We get our average score. Now the goal of this, we want to maximize f, which means to maximize the average score and just to maximize that function. So now instead of having to deal with this nasty word problem that we don't really know what to do and how to solve, we can just solve this mathematical equation.
So how can we do this? We know that there is a three-dimensional function f that inputs latitude and longitude and outputs an average point score, but we don't know what this function is. So first, we need to figure out what this function looks like. Then all we need to do is find the maximum of that function, and that will tell us where we should guess.
So step one is we need to determine GeoGuessr's scoring function. So I thought, surely that's just available online, right? Surely we can just Google that. And Anika told us that unfortunately that's something we cannot share. So we're gonna have to find it ourselves. So what I did is I went on the world map in GeoGuessr and I played maybe like 50 rounds and I recorded my score for each round and the distance away. And I got this really nice exponential curve. Now here's the equation for exponential: y equals a times b to the x. Now we can plug in our axis labels, miles away and average score. to get this is our equation for resulting point score. Now, let's say miles away is 0. Then b to the 0 cancels out to 1, or it becomes 1. A times 1 is a. So when we're 0 miles away, we should get 8 points. Why don't we just play GeoGuessr? What is a? 5,000 would be. So we got this equation. Point score is 5,000 times b to the power of the miles away. Now we're left with this little variable b. What could this possibly represent? Well, GeoGuessr has different maps, and some are more difficult than others. Let's take Monaco, for example, a country that's 2 miles long at its maximum. If you guess 2 miles away from the true location in Monaco, you're really bad. Meanwhile, if you guess 2 miles away in the US, for example, which is thousands of miles long, that's really good. That might know your score of 4.9 thousand, which is great. So this parameter b tells us the difficulty of the country. So we could do a curve fit on this to find the difficulty factor b of the world map. Or let's transfer it to the US map. As you can see, the curve becomes a little steeper and b shrinks a little bit. Or if we go to Luxembourg, the curve shrinks a lot, and b goes down to 0.8 from 0.998. Now, we're not sure if it's exponential. It just looks like a line. Well, let's scale this parameter up 150 times. Instead of 5,000, it now goes to 35, and we see we preserve this nice exponential fit. If we graph a bunch of these locations on a map, on a graph, we can see how the smaller the country gets, the steeper the curve is, and the lower the b parameter goes. Now, just an interesting tidbit. Here's Argentina, here's Chile. Here are their difficulty scores. They're really, really similar, almost identical. However, Argentina in area is about 4 times bigger than Chile. So this tells us that our difficulty parameter depends mostly on the country's length, which is nearly identical, not the area.
Let's return to our example of Australia. As GeoGuessr kindly informs us, there are 650,000 locations with Street View coverage inside the country, which is to say 650,000 coordinate pairs. Now, let's say we hedge a guess where you guys all guessed in New South Wales. Well, with everyone's favorite, the distance formula, we can convert each of these coordinate pairs into a single number, a distance from our hedge. But look what we have. A distance from the true location. Plugging all of these 650,000 distances into the GeoGuessr scoring formula we just derived, we can turn this into 650,000 point scores. These we can simply average out, obtaining the average point score associated with our hedge, our hedge here over the region of Australia. Now, this is absolutely perfect in theory. Everything relies upon us having this long list of the 650,000 coordinates of every single Google Street View location. However, we can't get this. After all, Google provides no easy way for us to obtain this list, and so everything else has to be theoretical. With our newfound, but sadly theoretical ability to calculate the average point score for every possible hedge, we now have our mystery multivariable function as before, but we can, with new knowledge, plug in a latitude and longitude point and uncover its average point score. This is still a pretty time-consuming process, as remember, we're dealing with 600,000 possible locations. Let's say each average score calculation takes a minute. So every minute, you can sample a point on our mystery 3D graph, and your goal is to find the highest average point score you can possibly achieve.
So one way to do this is we would just start randomly plugging in locations to hedge. So it's like, if we hedge here, what's our average point score? If we hedge here, what's our average point score? How about here? How about here? Now, there are a few problems with doing that. Firstly, this would be horrendously inefficient because Australia is big. You're not going to be able to plug in that many points. And if each one takes a minute, you're going to run out of time really quickly. Secondly, you're not going to know when to stop. With this, let's say you try hedging here, you get 2,500 points on average by hedging there. Is that the best you can get? What if you can get 4,000 with some awesome place to hedge? You wouldn't know. So you would just keep going and you wouldn't know when to stop when you had actually gotten the best possible hedge. So how can we do this in a more educated way? Thankfully, that method already exists. So I present to you gradient descent.
Let's first take apart this term. All gradient means is slope. It's what we call a slope in 3 or more dimensions. The slope of a regular 2D curve at a point is the slope of the tangent line at a point. And this slope is just a one-dimensional vector, a single number. Meanwhile, The gradient of a 3D surface at a point is the sloping of that tangent line, of a tangent line plane to that point. And it's a two-dimensional vector composed of the slope in the x direction and the slope in the y direction. The second part of the gradient descent just means going down. So this complicated technical term really just means going downhill. In our particular case, we're more interested in going up, not down, to find the maximum possible score, 5,000 instead of the minimum. So we'd be more interested in gradient ascent. The process is going uphill. It's the same problem, however, involving the same mathematical techniques. Well, here's a function for the simplest kind of gradient descent. How does it work? So we take 1 point P on, for example, Australia. Then we're going to calculate the gradient of it, which is what that at that point, which is what the upside down triangle means. Then we're going to multiply it by how far we walk in each direction, how far we go uphill, which is alpha. And then we add it to our point again. And we keep doing this over and over and over again until when it reaches the peak, the gradient at that peak is 0. And so it can't add, it stays the same.
If you imagine a little hill like this, if you look at the slope as it goes up, first it's gonna be a really steep line, then it's gonna level out until it's flat. And then if you press the curve, it's gonna go the other way again. Yeah. So, yeah. Yeah, more too. Okay. So let's step back and look at how far we've come. We began with the video game, GeoGuessr, and a problem. How can we optimize our limited information hedging? We turned this into a word problem, which we then turned into a math problem. So then this left us with 2 clear steps to follow. First, we need to find this function f that calculates the average score. Then we need to maximize it. So we found this function f by first looking at the GeoGuessr scoring formula with statistics to use our curve bits. And then we looked at Australia, looked at all the points there, calculated our locations and our average point score. Sorry, I got cut off. Yeah, and then finally we found the maximum of this function using gradient descent, a technique from multivariable calculus, if you'll believe it, and machine learning, allowing us to move and descend along a curve to the curve's extreme. So, however, we're not done yet. There's one more kind of leap of intuition for us to take. So far, we've only been looking at single player hedging. So if you have one person, where do you want to hedge? However, GeoGuessr also has a team mode, where you can have teams of 2 or 3 or 4 or more people input guesses. Then all GeoGuessr looks at is the closest person on your team's score or distance away, and then turns it into a score. So instead of 2 coordinate inputs, if we have multiple people, we can have 4 coordinate inputs, my 2 and my teammates 2, or 6 inputs if there's 3 people, or 8 inputs if there's 3 people. Sorry, 4 people. And all those inputs would lead to only one output. So that would mean our average score function would be 3-dimensional, or 5-dimensional, or 7-dimensional, or even 9-dimensional. Now, the beauty of this gradient descent algorithm is that it can work in any number of dimensions. So even if we have some 9-dimensional, super complicated average point score, we can still just look at the gradient at each point, go up the gradient, and find its maximum. So, yeah, our presentation uses methods from statistics, methods from multivariable calculus, methods from machine learning, all to let us play better at video games. And I think that's pretty cool. Thank you.
Thank you.
So our next dynamic duo make a fantastic team, which is something that was evident to us straight away from their audition.
And so from their audition, they wanted to really explore different concepts of infinity. They finally landed on using the famous analogy of the Hilbert Hotel. Something that's impressed Rachel and I from the very beginning is the attention to precision that they've had when discussing this really abstract concept. And we've just been so honored to work with the 2 of them.
So it's our pleasure to introduce Amelia and Jasmine. I don't know why I didn't switch on me.
To go put the bottom button.
Hang on for just 1 second.
Nice.
Close up.
Okay, imagine it's Rachel's infinite birthday party. And of course, she's gonna throw an epic party with all her infinite number of friends. But here comes the question, where can Rachel host this party with this infinite number of people? The Infinite Hotel. What is it? As you might have guessed by the name, the Infinite Hotel is a hotel that can host an infinite number of people, but it can only hold one person in each room. Looks like the hotel is fully booked, but that's okay. It's called the Infinite Hotel for a reason. If Rachel is going to have her birthday party here, first we need to make sure she has a room to stay in. To help us understand how we're going to move the rooms or move the people in the rooms, we're going to look at the first 5 rooms. But before we talk about the solution, talk with the person next to you about your ideas.
Yeah, I
Are you?
Okay, are you guys ready to hear our solution? Okay, so to do this, we are going to move each person down 1 room. Or the number n plus 1. So the person in room 1 would move to room 2, or 1 plus 1, and the person in room 2 would move to room 3, or room 2 plus 1. And because this is the Infinite Hotel, this process will continue all the way down until room infinity, and the person in this room will move to room infinity plus 1. And here is what the rooms look like after the switch. And we know that the Infinite Hotel itself didn't expand, but we were able to make room for 1 more person. And this tells us that infinity is equal to infinity plus 1. Okay. So, oh no. A bus comes up, and in this bus, we've got Rachel's infinite number of friends. So now, of course, we have to get them situated in the hotel as well. Okay, so here are your friends. Talk to the person next to you about how we might accommodate all these people.
make everybody. Double their. Everybody's traveling to finance.
Hey, guys. So,
Also, 1 goes to 2 goes to 4.
okay, so we know that there's an infinite number of odd numbers and an infinite number of even numbers. And we could get any number to be an even number by change it to an even number by multiplying the number by 2. So we can use this to our advantage by moving everyone already in the hotel to a room that is 2 times their original room number. So as you can see, Rachel's moving from room 1 to room 2. The person in room 2 is moving to room 4, and so on. And that way we can move in all of Rachel's infinite number of friends into the infinite number of odd rooms. And this process would theoretically continue all the way up to room infinity, and that person would move to room 2 times infinity. And so this is what it looks like after the switch. And given that the hotel did not change at all during this process, we can see how infinity is equal to 2 times infinity. Here's where it gets a little complicated. Like Rachel, her infinite number of friends are also very popular. And they decide to invite their infinite number of friends. So the hotel manager looks outside his window and he sees that an infinite number of party buses with an infinite number of people in each have pulled up to the hotel. So how will he move everyone into the rooms? Talk to the person next to you about your ideas. Before you talk about your ideas, remember that in the first scenario, we used addition, in the second scenario, we used multiplication. So what operation might you use this time?
Nothing against. Some of the math is on. Yeah.
Okay, now we're going to talk about the solution. If you guessed exponents, you are correct. But not only are we going to be using exponents, we're also going to be using prime numbers. And you might be wondering, what does prime numbers have to do with this? But we know that any prime number raised to an exponent is unique to all other prime numbers raised to any exponent. So every single time we do this, the result will be unique, meaning that we'll never overlap rooms. So to organize everyone into the rooms, we first have to start by moving around the people currently in the hotel. So we will assign them to the first prime number. This means that the person in room 1 will move to room 2 to the power of 1. The person in room 2 will move to 2 to the power of 2, and so on. And the exponent is either the room number they are or the seat number they are on the bus. So now that we moved around the people currently in the hotel, we have to move on to the buses. So the first bus will be assigned the second prime number 3, and the person on the bus, the people on the bus will be assigned to the prime number to the exponent of their seat number. So for example, the person on seat 1 on bus 1 will be assigned 3 to the power of 1 or 3. And this will hypothetically continue all the way up to the infinite bus, which will be assigned the nth prime number or infinite prime number raised to their seat number. Okay, cool.
So, Rachel's party is out of this world. So, some aliens from a distant galaxy have heard the news of this wonderful birthday party, and they're all pulling up on this spaceship, and there's an infinite number of aliens crammed onto this spaceship. You can see here. But the thing is, instead of going by like names, they choose to be referred to by their infinitely long name, which is a combination of A's and B's, and they're all unique to one another. So everyone talk with your partner again. Is this even possible? And while this may seem a lot like the first situation with Rachel's infinite number of friends on the one bus, the aspect of them not having seat numbers, they're just standing on this big spaceship, and also the fact that their names are infinitely long with those combinations changes it up a bit. So think about that.
All right, Sam, what's going on?
I feel like they could just add people on it by one.
Yes, assign. Like class of names, each class of numbers, like set of names, set of numbers. Like first we did this number equals two number, numbers equal, or number equals two times number.
Well, I wonder, well, so you have. Like. Richard, do you know?
The hotel is feeling a little bit overwhelmed.
No.
So he said, we know we have to be hospitable to these extraterrestrial guests. So he kicks everyone out of the hotel. Sorry, Rachel, your birthday party is canceled. Okay, so because he's really stressed out about all these aliens, he has created a theoretical spreadsheet. And here's the first 5 rows with the first 5 letters of the first 5 alien names. But obviously this continues down and on for infinity. So basically what he does is he takes a look at the first letter from the first alien in room 1, the second letter of the second alien in room 2, and like the third letter from the third alien in room 3's names. And what we can do is we can flip these letters. So the A's will turn to B's and the B's will turn into A's. And the issue is then we will have a combination, a letter combination of the name of a completely different alien that we haven't recorded before. And this would continue on and on, even as we go on infinitely long. And this creates an issue because every single time we continue this process, the new alien's name would be off by at least 1 letter because of the switchings. So unfortunately, there's no way for us to accommodate these aliens in the Infinite Hotel. What does this analogy show us? Why should you care? So this analogy reveals that some infinities are greater than others. While we are able to fit an infinite number of friends, their infinite number of friends, and Rachel, of course, we were not able to host the infinite number of aliens because they were uncountable. The fact that their names were infinitely long and there would always be another alien that exists, even if we hypothetically were able to write down all their names, it shows us that the Hilbert Hotel could only deal with the lower levels of infinity. And no matter what your math level is, how familiar you are with the concept of infinity, and like what your prior ideas about infinity were before you came into this room, we hope that we were able to kind of challenge your thinking and help complicate your ideas of infinity and kind of explore this interest about stuff. Thank you.
Well, we're gonna do a brief intermission. If you need to go to the bathroom, grab some snacks, anything like that, we'll come back. 5 to 10 minutes.
I guess, I guess.
So the first thing we're gonna do is we'll start a random asteroid. And the inherent property underlying Markov chains and pretty much all these algorithms is randomness. And the idea is you want to start on a random asteroid. You don't want your, where you choose to start to influence your results. So our second step is we're going to flip a fair coin with a probability of heads of 1/2. And that's going to tell us whether we're going to move clockwise or counterclockwise. So if it's heads, we'll move clockwise, or we'll propose to move clockwise. We won't actually move there yet. And if it's tails, we'll propose to move counterclockwise. So our first coin is going to be heads, let's say. And that means we're going to propose to move clockwise. But we're not guaranteed to move there because this asteroid is smaller and we're on a bigger asteroid now. So we'd rather, most of the time we'd rather stay on this big asteroid and continue to explore it. So our third step, I guess, after flipping that first initial coin, is we're going to flip a weighted coin where the probability of heads is the proposal asteroid size, which is in this case 1/5 the size over our current asteroid size. So the probability of heads is going to be 1/5. And most of the time, this will be tails. In this case, it ends up being tails. So then what we'll do is we'll keep track of where we've been. So we'll start on asteroid A, and since we stayed here, we'll say that we were staying in asteroid A. And then we'll do this one more time, and then we'll get into a bigger example. So the first coin flip, which has a probability of heads of 1/2, is a tails this time. So we're going to propose to move to asteroid C. And then our second coin flip, which has a probability of heads of 1/3, because this asteroid is 1/3 the size of our current asteroid, is a heads. So that means we're actually going to move to this asteroid this time and leave our current bigger asteroid. So we'll move there, and then we'll update up here that we actually move there. And so now I'll move into kind of a bigger example that will end up running a lot faster. So we'll say we're on asteroid A. And of course, we can only see the 2 asteroids over here. There's 7 other asteroids that we can't see. And in the real world, there could be infinite number or a finite number of some sort, but one number that is not infinity of asteroids. And we wouldn't know, we don't know what the number is, or you don't have to necessarily know what it is. So our first coin flip, which is a probability of heads of 1/2, which it always does in this case, is a head. So we're going to propose to move down to asteroid J. And then because this asteroid is 0.86 the size of our current asteroid that we're on, we're gonna flip a second coin. And this time, surprisingly, it's a tails. And actually, when I render this, every time it gives me different results because it's actually using the random number generator in Python. So like, whenever I'm talking about, it just makes up essentially. So we're gonna stay on our current asteroid, and then we'll keep track on this chart where we've gone. So again, in our first, our flip this time is a tails, so we'll propose to move counterclockwise. And since this asteroid is half the size of our current asteroid, we have a probability of heads of 1/2, and this time it's a head, so we'll actually move there, and then we'll keep track that we've moved there in this chart. And I'll do a few more of these just to kind of show how it works, and then we'll go a lot faster. So asteroid B has a relative size of 1, and asteroid A, as you can see, is twice as big because originally when we were in A, B was half the size, so now A is twice as big. So our first coin flip is a heads, and that means we're going to propose to move clockwise. And because this asteroid is bigger, we're guaranteed to move there because you can't have a probability that's greater than 1. So it's always going to be heads, and that makes sense because if you're on a small asteroid and you propose to move to a bigger asteroid, you're going to want to move to that bigger asteroid. There's not really, if you propose to move somewhere that's bigger, you're going to want to explore that bigger asteroid all the time. So we'll move there, and then now I'll just skip over these next few, and then eventually. Okay, I think this is. So eventually it'll do actually 1,200 simulations very quickly. And you can see it's doing the same thing that method I've talked about, just really quickly, 60 times per second. And we're going to keep track of over here of where we've been. And ideally, we'll end up with a distribution here that shows the actual sizes between all of the asteroids. Because originally we could only see the 2 asteroids that were next to each other, that were next to our current asteroid. But eventually we want to be able to see like all of the asteroids and their entire population or sizes. So this is the distribution after 1,200 simulations. That we end up with. And this is the actual asteroid size. And these actually are very close, which is kind of sad. And a few other times that I've run this, they were a lot closer. Yeah, it's not terrible. I'll show you in a second how it ends up, what it approaches, but this, but due to the randomness of random number generators, like, and it's not really random, it's pseudo random in a sense. But it's random enough for this case. You end up getting different, distributions every time you run the simulation. So ideally you do more than 1,200, and I did, and I had to do 20,000. Just that took like a second on the computer. And you end up getting something that's much closer, and there's still actually a pretty big, it's really weird, every other time I would run it, it would be even closer, but this is pretty darn close to what you'd expect distribution to approach. So it's really cool to be able to like explore your asteroids. Of course, you're not actually going to be exploring asteroids because that's not how you not how you explore asteroids. It's just a fun example. So how do they actually use this, and why is it so useful? So the main reason, one of the main reasons is that it's really scalable. And in this case, we only use 10 asteroids, or 10, I guess, things that we were estimating parameters. But in the real world, you could be estimating hundreds or even more because computers are so powerful. And the best part about this is in this, example, we had one dimension. We were just looking at, a single astronaut moving around one, asteroid belt. But in the real world, you might be estimating like 100 parameters and like, 100 dimensions, which you can't obviously visualize. But a computer can, calculate and do all these simulations just as well. And that brings us into like the power of computers. I only did 1,200 right here, but you could do 20,000. You could do way more. And oftentimes, instead of doing one run, you'll do like 10 runs or something, starting at different random positions, and then seeing if they end up converging to the same distribution. So it allows you to do way more computers. And so now I'll talk about kind of how I've been using this method or this algorithm. So I've been doing it in my MARC project. And in my MARC project, essentially what I'm doing is modeling how birds respond to fire. So this is kind of just some cool photos that, or not photos, figures that are related to that. So what we're doing is before this controlled burn in 2017 or 2019, we collected a bunch of data using autonomous recording units, which are essentially just recordings of birds, and then they would get classified. And then also point count. So we would go out and count what birds were in the study area. And so you can see this, there was a controlled burn that was done in 2019. And this is what in the areas that are red is where it burned the most, and where it's blue, it didn't really burn that much. And then in 2021, I believe, in the fall of 2021, there was the huge Caldor fire, which probably everyone here remembers. It was super smoky, and that was the year there was like a ton of fires. And this is what the burn severity from that wildfire looks like. And you can see it's pretty much a direct overlay from the controlled burn. So wherever the controlled burn burned, it didn't really burn in the Caldor fire. So we have a bunch of data basically showing us like, before the controlled burn, what was it like, after this small burn, what it was like, and then after this big wildfire, what did it look like? So I'll show you right here an example of kind of how we've used, these the Metropolis algorithm to look at how black-necked woodpeckers respond to wildfire. So we collect the data through point counts and ARUs or autonomous recording units. And this is one simulation, or I guess actually 6 simulations, but a single markup chain Monte Carlo simulation for a single parameter. So kind of how we were looking at, one astronaut going around a bunch of asteroids. This is just a single parameter. And this shows each iteration. So you would start here and then you'd keep going. And then you would basically end up getting a distribution for that parameter. And this parameter is actually correlating the probability of occupancy, which is kind of how likely you are to see a bird at a specific point, and the burn severity. So a negative correlation means that the bird declined with fire, and a positive means that it increased with fire. And this bird actually is really interesting. It has a black back because it lives in burn forests almost exclusively. And yeah, they're actually, like, before the fire there were none, and after the fire they're everywhere. But this actually, the data used in the simulation was only from a single year, which is why. If I graph this, so this essentially these are just a bunch of points. You can graph it, I don't see, but on a distribution, and you can see where kind of the distribution lies. So we've essentially been able to use, this algorithm to jump around a bunch of asteroids. But instead of a bunch of asteroids, we're actually jumping around a distribution, in some sense, to kind of explore that whole distribution. So we were able to find that we actually had a negative correlation with fire, which was really interesting, and it's because we only had 1 year of data. If we had multiple years, we would definitely see a positive correlation. But with 1 year of data, it's basically telling us that, with the fires in the general area, you can't look at a site specific, burn severity to determine how birds respond. You have to look at like a more general area, because maybe the areas that we saw the birds on where they were nesting weren't burned, but they were foraging in the burned areas. So it's a little bit more complicated than looking at each point and how the burn severity at that point. Yeah, so this was a really cool way of kind of being able to take a single slice, and in the simulation we had, I think, like multiple hundred parameters that we were estimating, because each point was essentially its own parameter, and then that led into this other parameter here, because it's called a multi-level model, which is really cool. So yeah, that's my project or my presentation, and here's everyone that could say thank you to. So these are my two mark mentors, Jack and Darrell. Tom, Lauren, and Matt, they're actually the people who made the machine learning algorithms to classify the species from the recordings, because we had all these recordings up, and we essentially wanted to, be able to tell what was in them without actually having to like go through all of them and listen to them. So they made these really cool algorithms, and then Lauren also recommended this really cool book that is where I got this whole example from. It's called Statistical Rethinking. And it's very interesting. And thanks to Kevin for all of the amazing help with making this presentation not too rambly. Probably is, but. Let me know any questions or anything. Too rambly.
So is your hypothesis that if you had taken like 2 more years of data, the birds would return and you'd see a positive, like a growth in population?
Well, so we have more years data, but the model was only looking at 1 year of data, because we were just like basically verifying the model. And actually a separate model that only used the point counts did see a positive increase. And that used multiple years. But with a single year, it essentially shows us that like birds, they're probably nesting in sites that are not burned, because the trees are kind of destroyed. Really burned areas. But they're foraging, there's a bunch of beetles that are in the burned areas. But yeah. Yeah, so they pick up everything. There's like, I think 80 species or something that they're like, the model is trained to classify.
So why did you show us the results for the versus?
Because this is a particularly interesting one, I think. We could do this for every single species. We've done this for like every species, but they're all separate models in a sense. So we have to run it with separate data each time. So the model essentially looks at, for one species, how does it respond to fire, essentially. But you can run it, for another species and see how they respond to fire. Yeah.
Is the algorithm picking up audio? Like, is it the bird sounds? Is it
Well,
video of the birds? How is it?
The algorithm for the machine learning algorithm is separate from the Metropolis thing, but yeah, so essentially what it does is it takes a spectrogram which is basically like a photo of the audio, if that makes sense. So like the frequency over time. And then it essentially compares that photo to like known spectrograms for other species. And the way that, and they have a really cool algorithm where it's able to like, essentially if there's multiple things calling at once, it can pick them out, which is really cool. They have a really cool like paper they wrote on that, but yeah, so if there's multiple birds calling, it essentially like compares that photo of the spectrogram to like known recordings of that species. Yeah.
Thank you.
Yeah, we have to do it. Audio.
Okay.
For this one. Great. While Kevin is retooling our doing audio here, I'll talk a little bit about our final presentation of the evening from Luca and Cece. These are two musicians here at MA who were really interested in checking out why human brains hear sounds as either pleasant or unpleasant. And they've even made a short composition for us that demonstrates some of their learnings, which is pretty exciting. They're going to dive deeply into some of the mathematics of different styles of tunings, particularly Pythagorean tuning, and why that creates sounds that are a little bit.
Kind of just always struck me is that as someone who listens to a lot of music, as someone who plays guitar, it's really hard to write and compose music without knowing a whole lot of music theory. Like you'll end up just like playing a bunch of notes and they'll like just sound horrible. So there is some like elements of notes that sound good and some that don't. And so we kind of go into that.
All right, so we have two audio clips here. One is 440 hertz played at the same time as 622 hertz. The other one is 288 hertz played at the same time as 432 hertz. Those are not arbitrary numbers. You will find out why later on. I see Fred going like. So we're gonna play them together, or we're gonna play one, and then we're gonna play the other. We want you to think about what you noticed, how you describe the sound, any words, feelings, associations. There are no wrong answers. After we play them, we just want to hear like your knee-jerk reaction. What does it make you think of?
All right. So here's the first one.
Uh-oh.
It's coming.
Surprise, those hertz values have silence. There you go.
Your age test. How did you all feel about that?
What are you guys thinking? There we
There
go.
we go. Yeah. All right, I'll play that one more time just in case. All right, and here's the second one. Play that one more time. Okay.
All right, anyone want to shout anything out? What are you guys thinking? I don't think I like the second one. Oh. That's the data we're expecting. Get out of here, get out.
I noticed that for clip 2, the second number is 1.5 times the first number. So there's some math involved.
That is the factor, that is.
That number 2 sounded more harmonious.
Yeah.
Ian, what did you say it reminded you of the other day? I can't remember.
School bell or.
Yeah.
Jarring.
All right. So that brings us to the ideas of consonance and dissonance. So essentially consonance means two tones sound good when played together, and dissonance means two tones sound bad when put together. But it turns out that the definitions of these two terms and exactly like what constitutes something as consonant versus dissonant, it's more arbitrary than you'd think. There's no exact definition of when the two separate. One thing of when like consonants becomes dissonance. The definitions have changed throughout history.
And the other disclaimer that goes with that is they're also different depending on location, what era of history you've existed in, where you live, what type of scale, what types of music exists. So it is also the types of consonants and dissonance we're going to be comparing today are going to be a totally different idea from what you might compare in, Gregorian chant if you were alive in that area and had a slideshow. But that's sociology. So we're going to focus on the here and now.
All right, so focusing on dissonance, something that creates dissonance between two tones is something called a beat frequency. So if you play two sound waves whose frequencies are close but not exactly the same, you're going to hear this kind of pulsing effect between the tones. And the way you calculate the frequency of that pulsing, how often per second that pulsing happens, is you subtract the first frequency from the second one. So for example, if you have a 700 hertz wave and a 690 hertz wave, then you would have a beat frequency of 10 hertz. So just an example of that, this is 288 hertz and 293 hertz. So the beat frequency here would be 5 hertz. Oops. There we go. You can hear it almost sounds like a UFO, like a sci-fi movie or something. And so the higher beat frequency you have, the less pure sounding that interval sounds to the human ear. So that's kind of interesting. And so here we have a graph of the first two clips that I played, the one that sounded really bad, the one that sounded more pleasant. So it turns out that you can model these with sine waves. So here, so I've scaled this down by a factor of 1,000, so it's a little bit easier to visualize. But I've set this red wave here to a 440 hertz wave, and you do that by having it be sine of 2 pi times the frequency times t, t being the x-axis. And then the other tone would be sine of 2 pi times the other frequency, in this case 622. So in Western music theory, that interval is called a tritone, also known as the devil's interval. So it sounds a little more off to our ears. And you can see that if you count the cycles of these waves, the places where they line up along the x-axis are they're a little harder to find. And if you zoom in, you're going to see that they actually don't line up exactly. Whereas down here, I have 288 hertz and 432 hertz, as Victor pointed out. That's 3/2 times 288. You get 432. So if you count 3 cycles of the blue wave and 2 cycles of the red wave, you see that they line up over here. And then again, they line up over here. I've marked those places with a black line. So.
All right, we're going to talk about 2 different tuning systems, which Taylor alluded to. So first of all, how many of you have ever played an instrument of any type in your life? That's impressive. Wow, okay. So equal temperament is one that even if you have never touched an instrument ever, you are incredibly acutely familiar with it because it is the temperament tuning system that all Western music is written in. So anytime you turn on the radio, anybody's ringtone, any kind of music you hear is more often than not, almost definitely going to be in equal temperament tuning. In this tuning system, 1 octave, which is a comparison of a bass note to the octave note. For example, you could do 440 hertz and 880 hertz. If that doubling in hertz, that's what makes an octave. Is split into 12 exactly evenly spaced semitones. By comparison, Pythagorean tuning uses ratios of powers of 3 to 2 for each of its 12 notes. We saw a demonstration of the major fifth, the frequencies of the major fifth, with what Victor pointed out in that second interval we looked at. And so we're going to play an example of a chord in an equal temperament tuning system, and then a chord with theoretically the same notes in Pythagorean tuning. Notes have the same name, but they will have slightly different frequency ratio values, and If you listen, you can hear a difference. Listen for, especially in the Pythagorean tuning, you'll hear an extra sort of ringing that comes from that closer like perfection in the notes.
Okay, so this might be hard to hear. The difference is very slight, especially to an untrained ear, and also the audio is just kind of quiet. It's kind of quiet also, so. I'll play that again. So it's slight, but there is a difference. And if I were to map out the frequencies, then you could see that. So
You could hear it, don't worry, now you can see it.
we're gonna dig a little bit deeper into that in a second.
Okay, so Pythagorean tuning is represented by the blue line on this graph. Equal temperament tuning is represented by the red line. And so each octave, you can see that the first one it has in here is an A. An A, again, it doesn't matter where you start on the note, as long as it gets octave, they're going to line up because Pythagorean tuning is the ratios that get you from 1 Hertz value to that Hertz value times 2. The equal temperament tuning, while you stop at different points along the way, you're going to start and end at those same values. So that's where that will line up. But the further you go, the more notes you incorporate, the bigger that discrepancy gets. You can see how close those sounds are at the beginning when you're comparing only a few notes to how much larger that discrepancy gets. And if you look, you can notice the equal temperament tuning being the even spacing of all those notes is actually just the best fit line of all those Pythagorean notes. And that will continue for every note that you can possibly play, aka every note that's audible to the human ear.
Okay, so this bit got cut out, but in case you were wondering, the x-axis over here is frequency. So this is counting 50 Hertz, 100 Hertz, 150, and so on. Yeah. So here we have the graphs of the Pythagorean perfect fit and the equal tempered perfect fit. So you can see again, this is just a reused graph from earlier, but if you count 3 cycles of the blue wave, 2 cycles of the red wave, they line up exactly here at one point along the x-axis. So again, I've included the graph or the functions over there being d of t because it's a d and a of t it's an a. And then you have that 3/2 times 288. And then down here for equal temperament, you can kind of see that if you count 3 cycles of the blue wave, 2 cycles of the red wave, you end up here. It looks like they line up, but actually if you zoom in closer to the x-axis, you can see that they cross over here. They don't actually touch along the x-axis at the same point that they do in the Pythagorean interval.
All right, so now we'll get more into Pythagorean intervals. So an interval refers to the distance between 2 notes, which in turn refers to the ratio of the frequency between 2 notes. So a lot of you raised your hands and you played an instrument. How many of you played a string instrument? Guitar, bass, violin, cello? Count the room. So you can visualize this as the ratio between string lengths. Imagine I'm holding a guitar, I strum 1 open string, it's whatever that string note is that's been tuned to. I put my finger down on the fretboard on that long neck of the guitar, I strum the same string again. That second note will be higher than the first note. Why? Because with my finger, I've shortened the length of that string and changed the ratio, making the note higher. And so intervals with exponentially smaller ratios are more consonant, and intervals with exponentially larger ratios are more dissonant. We have 4 examples here: perfect fifth, major second, minor second, diminished fifth. You can see the numbers, that pattern, the 2 and 3, and then you can also see, especially in the expanded form, how they get more complex. There's those exponents, those ratios are larger, and then we're also going to play them. So you can hear those differences. Again, it is in order of the most constant sound we have here to the least constant sound we have here.
And then that effect of being most to least constant is going to be amplified by the fact that we're playing them one after another. So we're playing a consonant one and then a less consonant one. It's gonna sound even worse because it was played after one that sounded good. So hopefully you'll all hear that. Next one.
All right, so now we're getting to the title of our presentation. How do you compose a perfect song? So we've talked a lot about consonants and how it creates a more pleasing sound for the ear. So of course, we're gonna wanna have a lot of consonants in our piece. But almost counterintuitively, we do need some amount of dissonance because like we're talking about, there is no cutoff where you can say, all right, these intervals are consonant and these ones are dissonant. It's all in comparison. One can be more consonant or more dissonant than another. And we do have objectively the most consonant one in existence and the least consonant one in existence in a 12-note scale, which is what we've been using and what the Western world uses. But other than that, you cannot split them into two camps. It's only through comparison. So we need that dissonance in order to create the consonants in some way so that you can hear it. The other thing that the human brain really likes, for reasons that we have not researched, but that we know, is that the human brain really likes resolution, which is very simply when you play something dissonant and then play something more consonant afterwards. You resolve the tension that's made by that dissonant sound. So now we're going to play for you our song, The Perfect Song, the pinnacle of humanity.
It's never gonna get better than this.
Yeah, briefly cool mention, you saw it here first, folks. Beethoven is rolling in his grave.
Somebody got us a concert.
This is the peak moment. We're gonna play. Okay, but so we made this 4-measure, about 10-second composition to demonstrate. And so we've got a couple of details. We've got tempo, sound markings, what key it's in. All that is arbitrary. If you can read music and you're thinking about that, forget it. It does not matter right now. What we are looking at is we've got our top line and our bottom line. And so in our top line, all the way through, we've got intervals that we can look at. And our bottom line, all the way through, we've got another set of intervals that we can look at. And so I've written out, without the qualities, but just, you know, our unisons, second, third, fourth, etc., all the way up to octave. So unison is just a stand-in for 1 first, basically an octave is a stand-in for 8 eighths. And so you can see in that top line, we've got lots of thirds, fourths, fifths, unison. Those are very consonant notes. In comparison, the 6th and the 7th are far less consonant. So that does create a little bit of tension. Bottom line as well, you can see we have an octave, we have more 6th, creating that tension. There's less numbers if you add them up in the bottom line, simply because there's less pairs. There's the 2 fourths have the star next to it. That is because one of these, and I believe it is that very last one, it's not actually a fourth, it's a 12th. It's an octave plus a fourth because of the way our brain hears those frequencies and those ratios. We hear it the same consonants as a fourth. That octave below it is a neutralizer functionally. And so, yes, this is our composition. Play it one more time for you guys.
We'll play one more time and then we're gonna call on a few people and ask your thoughts.
Yeah. Think back to the same questions from the very first slide. What do you think? What does it make you think of? How does it make you feel? Any kind of association? Again, no wrong answers. Yeah.
The resolution between the last 2 notes is really striking. It's very much what we expect to hear. Done, 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 and you know it's over.
It's like it's satisfying.
Yeah.
Yeah, definitely.
I hear end of a Disney movie.
Same exact thing.
It's always great.
I thought in the first half, it seemed to be kind of more pleasant and a little more dissonance or consonant. No, the opposite, but
Yeah.
dissonance in the second section.
Yes, that's definitely in there.
Okay.
All right.
Can you stay with Marvin Gaye yet? Letters on the way.
I made this on a Sunday, so it's day late.
Okay. All right,
That's our
thank you.
presentation.
I don't know where your head is right now, but I'm pretty shell shocked with everything we just learned. I feel like I definitely could guess where Mongolia is now. I still know nothing about music. But overall, what it, spectacular night, and I definitely cannot fathom what infinity is. I don't know where anybody else is there. But I just want to, thank you all so much for coming. First off, just here's my, my closing notes. Beforehand, I just want to recognize everything that happened behind the scenes. Thank you to Travis and the rest of the admin for all your enthusiastic support. We do this every year and it definitely doesn't go unnoticed. I really thank you so much. Justine and the communications department for spreading the word, hopefully getting it out there. We got some people on Zoom tonight, so thank you for coming out as well. The math departments for obviously all of your continued support, the families for supporting everybody who was participating tonight. She's not here, but Devin Hunzinger once again put together the math graphics for it. I don't think she's here, right? No, okay, but I wanted to give her a shout out. And then one more round of applause for, just so I don't forget anybody, Eric, Luca, Amelia, Jasmine, Mark, Luca, I already had Luca, Luna, Luca, Cece, Victor, and Sam. Thank you all so much. Our presenters and the math faculty would love to take a little picture with you all before you leave, and then we have a little bit of something, say thank you for all your hard work and effort. So thank you all so much. Thank you.